say is similar, you see the little remote control thing?
Yeah, it was on.
It's not on.
Did you screw this up now?
No, it's on. It's on.
It's on. So, today we're talking about similar polygons. If you hear the word similar, what's that mean?
Same.
Same what?
Shape.
Okay, I like that. So a similar anything, so we can do this with any polygon, which means what? What's a polygon? A shape, right? So when we talk about similar polygons, we're talking about similar shapes, and you said it's the same what? It's the same exact shape, but what? But different sizes. So what's true about similar things? They what? They gotta look the same, right? Because they're the exact same shape. So, but what's true about that small one compared to the big one?
The angles are the same degree.
Okay? So when we say it's the same shape but different sizes, what angles are we talking about, Riley?
Opposite angles.
What do you mean by opposite in that case?
Opposite interior angles.
So are you talking about opposite angles of one of the shapes?
Of both the shapes.
Of both the shapes.
Yeah.
Okay? And the opposite angles are what you said? Congruent. Okay? Hold that thought.
Corresponding.
That's what we want to talk about more, is corresponding angles. So let's stop. What's this mean? Corresponding. Yeah, so this is the same exact spot. This is really, really important. Okay, so corresponding angles are what? Congruent. So even though that we have two different size stop signs, what figure do I have? An octagon. So I have a big stop sign and I have a small stop sign, but they all would have the exact same angles. Okay? So the corresponding angles are congruent, but the corresponding sides, are they the same length? No. Obviously not, right? Because one's bigger and one's smaller. So the corresponding sides are what? What did we do in the first section? Opposite. What did we do in the first section? What did you do your homework on today?
Oh, portion.
Ratios, so they are proportional, right? Okay? So that's why we had to do yesterday's, so we could get to today's. Right? So you ever seen, I can't say the word, but it's a Russian doll, where you open up the Russian doll and there's another Russian doll inside, and then you can pull that one out and you can open it up. It's like Marshushka or something like that. So, but you can keep opening them up and you get the exact same thing. That would be similar figures, right? So that would be 3D, but it's the same concept, okay? And ours are just flat, okay? So, how do you, it's represented by what? How do you show similar? What's the symbol, I guess?
Arches, slashes.
Represented, no, how do I show that this octagon is similar to that octagon? There you go. Top of the congruent thing is a good way of saying it, but it's the little squiggly thing, right? I don't know what it's called. Okay. And we can do this with any shape again. Alright? But you're right. We would use then our arcs, and we would use, we're not going to use slashes now because our sides aren't congruent. They're proportional. That's a really big concept you got to get into your melon. Alright? So you're going to take your corresponding sides and you're going to try to show this by making a ratio. Alright? Let's see here. Let's just draw, your octagon. Well, let's go back to a pentagon. Can you try to draw the exact same figure? So that's my pentagon, not very good. But now I gotta try to draw the exact same one, but just draw it smaller. Something like that, okay? So then we would go and we would name it. Again, how do I name an or a pentagon or any shape? I just start labeling the vertices, and then you gotta just make sure that you go in order all the way around, okay? So if we call this one A, B, C, D, E, and then we call this one what? F, G, H, I, J, okay? So we're gonna compare these two. We would then say, so one of the things that you're gonna have to do on the quiz and the test and your homework is to show corresponding parts. So when you're talking about corresponding angles, this is where somebody said to put on the arcs, right? Well, you can put on the arcs. Okay? Are all of these angles the exact same? Maybe, maybe not, right? It depends on what the shape is. If it's an octagon, would all of my angles in that octagon be the same thing? And so what would we call that octagon? It was a what kind of octagon? A regular octagon, right? Anytime you use that word regular, it means that all of my shape or all of my angles are the same. But in this case, we don't know that for certain. So as we go around, we start or we add another little arc as we go. Right? And this is just showing that each one is congruent to the one over here. I think you have 5. Okay? So the first thing that you're going to have to do is to show this. So again, you could say pentagon, and this is where it's important that you make sure you match up the corresponding angles with the other one. So A, B, C, D, E is similar, right, to pentagon. And now this one's really easy because they're what I would call the same orientation, right? They're sitting the same way. Well, let's just say that we took this one and we rotated it where G is on the bottom. Then you got to make sure that you match up the corresponding angles exactly right. So you can't just start, if we flip this one up here and I was up here and we started over here at A, B, C, D, and we can't just then say I, J, F, G, H. We have to make sure that they match up. Everybody see what I'm saying there? Okay. So then here, my pentagon would over here would have been, and again, we did it on purpose this way, but you just got to make sure. And so, realistically, we could go through, and if they didn't give us the pictures, they just gave us this. What would we call this? Okay, but is it a congruent? So we would call this a similarity statement, right? But you're right, it's the same concept as our congruent statement. This is my similarity statement. If they just gave me that, we could go through and we could figure out what angles were the same spot as the other angle in the two different pictures. That makes sense? Okay? From here then, this is what we did yesterday with the sides, so we're also then talking about the lengths of the sides have to be proportional. So again, so between the 1 arc and the 2 arc, we would have some number. Okay? We're going to make it easy on you. We're going to call this 10. If I call this 10 and I say then I'm comparing it to the same spot, which is between 1 arc and 2 arc, I'm going to make a ratio between those two, and we'll make it real easy, and we'll say this is 5. Okay? So, if they ask you to make a ratio between the lengths of the sides, you would then make sure that you set it up, and we would put 10 over 5, and then, obviously, we could reduce it into 2 over 1. Okay? From there, then, you would have to check to see that every group of every sides would have that exact same ratio.
So they'd have to be 2 of 1.
Right, so this one right here, if we said BC was, if this is 10, this one's got to be bigger, right? So let's just say this is 18, what would GH have to be? 9, okay? And so on and so forth, right? And if we can prove that all of these are true, so this one is 12, this one is 6, this one is 8, this one is 4, this one is 6, this one is 3, okay? If you can go through and figure that out every single time and that is true, then you're proving that these are similar. So even though that the angles might all be the same, your sides might be a little different. So you got to check every single group. That makes sense? So if they ask you to prove that it is, this is what you're going to do. And so once we figure out this, that they are similar, they're going to ask you to make ratios of the sides. So the ratios of the sides obviously are 2 to 1 with numbers, but basically what they're saying in this is to take the length of the side, AB, and what does it go with in the other figure? FG. And then I would have to go through and figure out all of those. And this is my ratio. So yes, it is 2 over 1, but they're asking you what are the sides. So then I'm going to go BC over what? GH, and then we would continue on, and you'd have to do all of those. Does that make sense? So if they ask you to write the ratios. Now, what's the most important part of the ratios? Is that when you do this, and you do that, this is the bigger one, right? And this is the smaller one. You just have to stay consistent all the way through. So if you do the bigger one on top at the beginning, it has to be the bigger one as you go through it and list all the sides. But you can also do the smaller one, okay? So you could flip it over, and if my first one, so Gabriel looks at it and he says, well, I'm going to do FG to AB. That's totally fine because those two sides are corresponding. But then because he did FG on the top, then his next one has to be GH is to BC. And then so on and so forth. That makes sense? And that's really important, that you always put the same shape in the same spot. Okay? Now, what's this number called? Any idea?
What number?
The one that I circled.
Scale factor.
This right here is called a scale factor. Okay? So what's a scale factor? Well, the scale factor is your ratio between, or making your comparison. A ratio showing the comparison or relationship, maybe, between figures, shapes, whatever you're doing. So we don't necessarily just want to limit it to figures. We could say shapes too, because we could do this with three-dimensional things, right? We talked about the Russian doll. That's kind of what it's saying. Okay? But again, we're showing the relationship of lengths, right? It's always about the lengths of the sides. There's no way that you could have multiple ratios, meaning different numbers. So if this is 18 and they would have told you that this was 7, when they just change one of those, that makes the two shapes not similar.
So
That makes
the whole
sense?
thing would be not similar?
So the whole thing's not similar. Okay? Only one of them. So that's where you got to make sure that you test all of the ones that you possibly can. Right? So we come back here, where do we have this one? 6. Now, as a scale factor though, it's really important. There's always 2 scale factors. Why do we say this? Say it again, Cam, louder.
You can do the bigger one on top of the small one. on top.
Exactly right. So, when we say this, it's the big over the small, or the small over the big. So if we did the big over the small, ours would be what here? 2 over 1. If we did the small over the big, it would be 1 over 2. So my scale factors are what to each other? Reciprocals, right? And that's really important. So again, if I'm going from the bigger one to the smaller one, my scale factor is always going to be what? Greater than 1. X, meaning my scale factor would be greater than 1. If I'm going from the smaller one to the bigger one, then my X would be less than 1. It's going to be a true fraction. So you're going to have more than a whole number here. You're going to have a basic fraction. And this would be like what you're going to do for something called a dilation, right? I think we've talked about dilations before with our eyes, right? This is what, I can't say that word, an eye doctor would be good at knowing the difference of how to make your eyes go big and small, right? So when your eyes dilate, they get ginormous, so they can look at your veins and stuff inside there to see if you're got something wrong with you, right? Meaning your eyes, not.
Yeah.
I didn't want you to think that we were saying that you're just got something wrong with you.
They called them not normal yesterday, so.
I did what?
They called them not normal.
Not normal.
Not you.
Alright, so how do we use our scale factor? That's what we're seeing. You can do this with dilations, but you could use this in chapter 9, if we would actually get to chapter 9 and do chapter 9. You can do dilation by doing this to an ordered pairs on your coordinate plane. So instead of drawing it freehand right here, we could plot one of these shapes on a coordinate plane. And then we would know each of the x, y's of those vertices, right? Well, to dilate it then, we would take each one of those points and multiply it by 2, and then we would show the bigger one to the smaller one. See what I'm saying? So then you could affect every single vertex by that dial or that scale factor, and you could either blow it up or you could shrink it. Okay? And that's kind of what you would do. A lot of years we don't get to chapter 9. Okay? So when you talk about scale factors, you basically can do this with a lot of things. You can do this with the sides, just in a normal, everyday figures. You can do this with perimeters. If you think about a perimeter, we're just talking about the what? All the way around the outside, right? Okay? So, if I knew my scale factor between the two, but I only knew the perimeter of one of them, I could set up a proportion to figure out the other perimeter. Because a perimeter is basically just setting 1 to 1, adding up all of my outsides. Okay? I can also do this with area, but if you think about area, what happens if you take an area of a shape?
So two
Squared.
It's squared, right? So if you're going to do this and use the scale factor to define an area, you would actually have to square all the parts that you're going to do this to. So you'd have to take your scale factor and square it. And then if we get to volumes, which we'll do later on, you'd have to do what to it? Cube, right? So basically you can use the scale factor to find a lot of things, but you just got to make sure that you manipulate it in the right way. Now again, this isn't what anything we'll do today. We're only going to do the perimeter today. So if you want to do this one with the perimeter, actually leads us to a theorem. And our theorem is 7.1. Okay? If two polygons are similar. So again, if they say they're similar, you can't argue it. Their perimeters are also similar, or are proportional. To the scale factor. And you actually have to do this in your homework. I think you actually have to do this on either the quiz or the test too. We'll show you that in the exam, okay? Okay. So again, like I said, you could do this, and we will do this when we get to areas, and we'll also do this when we get to volumes. But then you just have to remember to square it. So Brandon says how you do that, and we'll show you that in just a second.
How do you be proportional?
How do you be proportional? What do you mean?
Like how does it be proportional to the scale factor?
I'm going to set up a proportion. We'll show you that. That's kind of what he's asking to. All right? So, any question with the words? Jackson, turn, please. So, here's the kind of problems that you're going to end up having to do. If triangle ABC is similar to triangle RST, okay, they tell you that, you cannot argue it. Right? If it's said, it's done. List all pairs of congruent angles and write a proportion that relates to corresponding sides. So in this case right here, they don't put any of the little arcs in your triangles, right? So they don't show you what angle is similar to what angle by the markings that we did up here, right? But they give us a similarity statement. So if I asked you what angle is similar to angle B, you would say what? Because why? It's in the exact same spot, okay? And again, this one right here is really easy because the two triangles are set up the exact same way. If you would take this second triangle right here and rotate it where the S was on the bottom, then it does get a little confusing maybe a little bit, okay? So when they say write a proportion that relates to corresponding sides, now we're going to do these fractions right here. So somebody give me one proportion that would work, or a ratio that would work. AB is over RS. Everybody agree? So if he says it that way, then another one has to be what?
AC over RT.
AC over RT. Okay? And then if somebody would have started out by saying RT over CA, that's okay. But then I have to do it that way the whole entire time. That doesn't matter. Everybody understand what she's saying? So if Gabriel says RT and Mr. Cleach says TR, we're still talking about the same side. That doesn't matter if you flip-flop the letters. Okay? Can I tell what the scale factor is in this one? No. Right? There's no way that I can do it. There's no way that I can set up a proportion. Okay? Everybody okay with that one though? You will have to do that on your quiz too. Alright, so Tan is designing a new menu for the restaurant where he works. He wants to determine if the size of his new menu is similar to the original menu. If so, write a similarity statement and figure out the scale factor. So, how the heck do I do this? So I'm going to basically take my, whatever they give me, and I'm going to say, in my first menu on the left, it does not matter if I do 10 over 12 or 12 over 10. But I'm going to set that equal to, the other one was, what are the numbers?
12 over 14.
12 over 14?
Yeah.
So, are those two ratios equal to each other? No, right? So I either reduce or I do what we did yesterday, right? Do the cross products and see if they're the same thing. So if this is no, are they similar? No, right? Because basically we can already tell that realistically they're rectangles even though they didn't put a box in the corner. Okay? The next one I think actually works. So if I do this, is 10 over 12 the same thing as 8 over 9.6? This is where you might have to punch it in your calculator. Is 12 or 10 divided by 12 the same thing as 8 divided by 9.6? Yes?
Wouldn't you do 10 to 8 and then 12 to 9.6?
You can do it either way, basically. You can do it basically. So, right, because then the diagonals would still be the same. So I did it as menu to menu. You're doing the top to the top and the left to the left. Does it work, Gabriel?
Yeah.
Yeah. Okay, so here's the question. What's my scale factor?
The ratio,
And which is what?
12 to 9.6.
12 to 9.6 or 10 to 8. And then you should try to reduce them. That make sense? What?
So 5 to 4.
5 to 4. Exactly right.
So you put 10 over 12.
I did 10 over 12 when I did my proportion. But if you're going to do a scale factor, then you got to go like the top to the top or the left to the left.
10 over 8 and 12.
So basically, I'm just doing 10 over 8. Is that the same thing as 12 over 9.6? So basically, I'm taking those two and multiplying them together and seeing if they're the same thing when I multiply them that way.
What if you just remove those two?
If you reduce them, that's fine. What the decimal is just harder. So if I'm going to reduce them, I'm just going to punch them in my calculator and see if the decimals are the exact same. And if they are the same, then I come back here and that is my scale factor. Well, it doesn't matter. Either one's the exact same thing. But I'm going to normally try to make it as small as I possibly can. They're going to be the same thing. What do you mean both?
There's always two scale factors.
Right, so you could have said it this way, or you could have said 8 over 10, and both answers would have been right.
Okay.
So in the book, I'll read like 1/2 and 2.
Okay, we don't put both?
No, you can do one or the other. Everybody understand what you're saying there? Okay. So then they get into mathematical ones, right? So this is, gentlemen, kind of what you were asking right here. So the most important thing of this is what? The two polygons are similar. Okay, so they already tell you that they're similar. There's no argument about it. Okay? So when I do this problem now, I'm going to try to find a set of sides that are corresponding that I can make a ratio on. So if I look at these two figures right here, where is one side that has a real number on both shapes? So my scale factor is what? 6 to 4. Everybody agree with that? Okay, so this one says find x. So here's x. If x is on this figure, where does x have to go in my fraction? Everybody understand that and understand why? So what goes on the bottom? 3. And then I just do my math. Right? So then I do 6 times 3 divided by 4, and that's what x is right here. And that's what I can fill in right there. So that's making my proportion and using my proportion. So when I do the y's, okay, go ahead. Sorry.
I was gonna say, can you reduce before you?
You can totally reduce if you want right here. Yes,
So
absolutely.
you can cross
Be
it.
1 over 3.
No, but if you're gonna reduce that way, I would reduce up and down, not diagonally. Because when you go diagonally, then you're actually doing your multiplication. Okay, so always, if you're gonna reduce something, I would turn this into 3/2 first. Okay? So with the y's then, I'm gonna use the exact same fraction. I'm still using 3 over 2. Now what am I going to do for my y's?
Y plus 1.
8 has to go where? On the top, and then y plus 1 is on the bottom. And again, if I have a quantity, what am I going to do? I'm going to distribute that through there. Okay?
So you need 3y plus 3.
3y plus 3 is equal to 16. Exactly right. Everybody agree? Okay? And I believe we can show you that this way. So there's my first one. Right? and then my y was this way. So again, they're just showing you what it actually is. So then somebody said, how do I do this with a perimeter? It's kind of an interesting problem, okay? So if ABCDE is similar to RSGUV, find the scale factor and the perimeter for each polygon. So again now, some people say, and Shayla kind of brought this up, well, how do I know which one I actually want to do? Do I want to do the big one to the small one, or do I want to do the small one to the big one? If they just say in general, you can do either one. In this one right here, when they say find the scale factor of ABC to RST, I'm going to do the little one to the big one, so I'm going to put the little one on top. Does that make sense? Okay, so how the heck do I figure this one out? Okay, so I'm going to look at the dashes, right? So if I start filling things in here, I know that this has to be 4. Do I know what this is?
No.
Not really. Okay? Can I figure it out?
Yeah.
Oh, yeah.
It's 10.5.
Okay, so this is 10.5, right?
And that is that straight.
What is?
Those two dashes.
So is this definitely 10.5?
No.
No, because remember, my two shapes are different sizes. So my lengths have to be different sizes. So how do I find this length right here?
I did 7 divided by 4. And
Okay, so I'm going to figure out my scale factor, which is 4 to 7, and then I'm going to do what?
7.5 over
X to 10.5.
X over 10.5. Why has it got to be this way? Because I did 4 over 7, right? So, somebody punch that in your calculator?
It's 6.
6? Okay, so if this is 6, that means this is 6, right? Now, if I look at this shape and see that the two sides are the same as the bottom, what conclusion can I make over here? I could make the conclusion that this is 10.5. Now, if I can't see that, now I'm going to do this theorem right here. Okay? If I figured out that this was 6 right here, which I did on the little one, can I figure out what the perimeter of that is?
Yes.
By just doing what? Adding them up. So what's 6 times 3 plus 8?
26.
So 26 is my perimeter of the what? Small one. So look, I know that my scale factor is 4 over 7. The perimeter of the small one is 26. I can use that same thing to find the perimeter of the big one. So that's what this theorem is saying right there. As long as I can figure out my scale factor, I can make a proportion with the perimeter. Now, we already figured out another way of doing the perimeter because we figured out that all of those were 10.5, so I'm just adding them up. But if you can't see that, then you can always use the actual proportion.
Did you just do 7 divided by 4, which is 1.75, and then divide that by 10.5? It's the same thing. What? That's what I did initially with that one. It worked.
He divided the fraction and then he just.
Okay.
It's something.
Sure.
It worked.
Well, not all of us understand your methods.
This is Jesus.
Yeah.
She's too smart.
Everybody understand the perimeter one though now? So again, like I said, you can do this to areas and you can do this to volumes, but if you're going to do this to an area, then you have to take your scale factor and square both the top and the bottom first. But again, we're not into that right now. We'll get into that later. Okay? Questions?
No, man. Just
I
this.
believe that is it.
Just this.
Now realize the first one you're doing all the parts.